Open the Xilinx tool, click on File, create a new project. Let me give the name as CORDIC_DUT. Click on Next. Here you can select any of the FPGA family. Allow me to select Automotive Spartan 3. Click on Next. Finally Finish. Now go to the left, give me a right click, click on New Source. Since we are discussing with respect to Verilog module, I am going to select Verilog module, give the file name to be CORDIC_DUT. Click on Next. See that Add to Project is tick. Click on Next. Again Next followed by Finish. This will create a default window. Let me erase it all and start writing as generating sine and cosine signals using CORDIC. Let me start with module. I am giving the module name to be CORDIC_DUT, followed by I need to have a clock signal. I must have a two output signal. One is your cos signal, one is your sine signal, followed by two inputs I must have. One is your input signal. I am considering input underscore x, followed by input underscore y. Finally I must have angle value, so I am considering an angle factor, semicolon. Now let me declare my protest input, which is nothing but a clock signal, followed by input. I am assigning with respect to sine values, so I am mentioning the sine keyword. Since I will be dealing with respect to parameter, so I am considering the width value, width minus 1 down to 0, followed by input underscore x, comma input underscore y. Now I must have one more input, which is nothing but a sine angle, which is of 31 down to 0, nothing but 32 bits. I am declaring to be angle. Finally, I am going to declare my output parameters, sine followed by width minus 1 down to 0, which is nothing but sine and cos. Since I said I will be dealing with respect to parameter, allow me to write the parameter value, width followed by, I am giving a constant value of 16 here for a 16-bit operation. Again I need to declare a wire, sine, which is of 32 bits, 31 down to 0. Since I will be using my lookup tables where I will be storing the values of the arc tangents, so for that purpose I am using this wire. I am assuming this to be arc tangent value underscore table. This will create a 0 down to 30. This will create a two-dimensional memory if you are much familiar with Verilog. So this will create table for the arc tangent values that are to be generated. Now I need to copy those values, those arc tangent values, which I have then converted into binary. So I will be placing those binary values. So here is the generated table of arc tangent values. These are the values which are being stored in the lookup table. You can observe, for example, if you consider with respect to 45 degree, the arc tangent will be 2 power 0. Similarly, for the next coming degrees, we will be declaring with respect to arc tan inverse of 2 power minus 1, 2 power minus 2, 2 power minus 3 and so on. So those converted binary values are these values, okay. Now I need to declare few registers. Before that, let me declare few registers here itself. Let me declare reg sine values, width down to 0, x with respect to 0 down to width minus 1. Again this will create a two-dimensional array, reg sine with respect to width down to 0, same with respect to y I am going to declare now, followed by 0 under width down to width minus 1. Similarly with respect to reg, signed. Now I am talking with respect to angle, so 31 down to 0 since we have taken with respect to 32 bit for an angle, followed by z from 0 down to width minus 1. Finally, for a quadrant value, I need to take a wire. I am assuming this to be a wire 1 down to 0. Let me name it as quadrant. Okay. Make sure that the rotation angle is within with respect to minus pi by 2 and pi by 2 of range. Since we will be talking with respect to fixed angle of rotation, the rotation value that we will be fixing with respect to this program itself, thereby this range will be applicable from minus pi by 2 to pi by 2 itself. After storing the values in lookup table, let me assign the value to the quadrant. Assign quadrant is equals to angle with one particular angle, 31 down to 30 I am assigning. Finally I am going for the procedural assignment statements now. Always at passage of the clock, begin. Let me take the case statements. So case I am declaring quadrant with respect to a 2-bit representation, 2 tick b 0 0 followed by 2 tick b 1 1. Let me consider, because no change needed is for these quadrant values, that's the reason I am keeping as 0 0 and 1 1. Begin. Initially x of 0 I am assigning the values to be input underscore, which is nothing but the input. Similarly y of 0 to be input underscore y, and similarly z of 0 with respect to angle. Now let me close this with end. Similarly now let me take 2 tick b 0 1. Again start with begin. Similarly for the x of 0, this time I will be taking minus input underscore y. Similarly for y of 0, I must take input underscore x now, and as usual for the z of 0 I am going to operate with the concatenation operation, for which 2 tick b 0 0 making an angle with respect to 29 down to 0. Let me close it, followed by end. This actually will make a subtract operation for the angle in the quadrant form. Now let me go for the third case, when the value is 2 tick b 1 0. This is the leftover, right? As usual begin. X of 0, let me give the value input underscore y. Similarly y of 0, for which the value will be minus input of x. Finally z of 0, again making the concatenation operation with 2 tick b 1 1 with an angle same 29 down to 0. Let me close it. Let me end this with an end, followed by end case. Finally I am closing this procedural assignment statement with. Now I need to run with respect to iterations, so I am going to take the keyword as genvar of I, which will generate few iterations. Generate, which is again one more keyword, followed by a for loop I am using, initially with I is equals to 0, ranging with I less than width minus 1, followed by I is equals to I plus 1. This will create a loop. Again within this loop I am going to write the construct begin some x y z I am considering. Wire z I am assigning to be signed, followed by wire signed with respect to width down to 0, x underscore shift right in order to perform the shift right operation, y underscore SR shift right. Now I am going to assign the values. Assign x underscore SR is equals to x of I, which perform the Verilog operator of shifting operation. Again with respect to assign, y underscore SR is equals to y of I, again perform the shifting operator of Verilog, followed by finally assign z underscore sign, which I have already declared here, is equals to z of I followed by the last bit 31. Now let me write this will determine the sign of the current rotation angle. Okay. Now let me write one more procedural assignment statement, followed by always at passage of the clock. Let me begin with, now this time the last statement that if you remember, which will be with respect to I plus 1, xi plus 1 is equals to z underscore sign. I am going to operate a concatenation operation. If the statement is true, then this is going to perform the operation plus y underscore SR. If the statement is false, it is going to perform this operation minus y underscore SR. Similarly for the y expression, I am writing the equation as usual, z underscore sign. If the statement is true, then y of I minus x underscore SR. If the statement is false, then this is to be going to get executed, y of I plus x underscore SR. Similarly with respect to z of I plus 1, this would be equating to z underscore sign question mark. Now with respect to rotation, right, now I need to take the table, I need to take with respect to the arc tangent value, since I am talking with respect to angle. So z of I plus arc tangent underscore table of I. If it is wrong, I mean if it is false, then we will be going for z of I minus arc tangent underscore table of I. So this condition need to get satisfied. Let me end it with end module followed by end. Let me end it this whole all end followed by end generate. Finally, I need to assign all the signal values to the, I need to assign all the signal binary values to the output, right? So I am going to go with the assign keyword. Assign cos is equals to x of width minus 1. Similarly assign sin is equals to y of width minus 1. Now let me end all with end module. Allow me to save this. Go to file, click on save. This has successfully saved. Okay. Now before running this, let me write test bench for this part. Now go to the DOT file, give a right click, click on new source, go to the Verilog module. Now since I am working with respect to test bench now, let me name the file name as testbench tb underscore CORDIC. Click on next, next, finish. Again let me erase this all. Since I am talking with respect to test bench for DOT, design under test. As usual, I am going to start with module name, module test bench underscore CORDIC. Now this time it is not mandatory to write all the time port list, since I am talking with respect to test bench. So no need for me to write again the port list. Let me continue. Since I have declared there with respect to parameter, I am talking with respect, I will be taking here local parameter local param which is 16 I have already given. This define the width of x and y. Okay, followed by I am going to take the register width -1 down to 0, for which let me take two inputs here as x in and y in. These will be acting actually as the output for the previous DUT, followed by reg which is 31 again down to 0, followed by angle, again reg with respect to clock signal, again reg, this time I am taking sine with respect to 63 down to 0, iterations, right? So I am considering to be I. Now wire width -1 down to 0, followed by cos underscore out and sine underscore out. Finally one more local parameter I am taking, local param gain value I need to define, right? So I am taking AN is equals to 32,000 divided by 1.647. It depends on the specification that you are doing. Here I am taking with respect to the gain of this value. Let me start initially with initial followed by begin for setting an initial values. Here let me remind you the project that we are doing with respect to fixed angle of rotation. So I need to make a fixed angle. So I am taking one angle value. Angle is equals to some tick B 0011 0101 0101 0101 0101 0101 0101 0101. Let me count it. 1 2 3 4 5. So total of 32 bits, right? Angle we have represented. So xn I am giving to be the previous value which is nothing but an. Similarly yn it would be 0, followed by clock signal. I need to generate a clock signal. Let me start with initially with one tick be 0. Now by using forever loop I will be able to generate the clock signal. Begin. After 5 time units I need to have a clock is equals to not of clock, followed by end. Again after 50 time units, again you can put a random values. Okay, this just representing with respect to timing delays. I need to define the angle is equals to tick B 0010 you can take any of the angle values being converted with respect to the arc tangent in terms of 2 power minus I. It's up to you to put the values of I with respect to 0 to infinity. Again after some delay of around 1000 time units, let me stop it with writing $right. I need to give a statement as finished simulation. It is much similar to your printout in C language, followed by $stop. Let me end it all. Initial we have placed the end begin, right? I am going to end that initial part. Finally the CORDIC, what is the DUT module name we have given for CORDIC? We have given CORDIC underscore DUT, right? Since we are linking this with respect to DUT, so I am copying this part. DUT some instantiation name I am giving to be C1, followed by clock cos underscore out sine underscore out x in y in and the last one angle. Let me close this. Finally one more initial I am writing for monitoring the output. Initial, this time I am going for $monitor, followed by time. This is not a needed one, you can, it's up to you to keep time or not. Cos underscore out, followed by sine underscore out, followed by angle value. Finally I am going to end with an end module. Let me save this. Now click on simulation part, click on your test bench part, click on run. width has not been declared. Okay, we got an error here, width has not been declared. Let me cut this and paste it here before the part so that I'm okay with it now. Let me save this, again click on run. Let's check now. Line number 3, test bench has no port. We are getting the synthesis as failed because we can synthesize a DUT file, but we can never synthesize a test bench file. In order to satisfy that, let me copy this all and paste it in model sim and check whether it is running it or not. Let me copy this all. Open your model sim. So model sim window is open. Go to the file. Click on new, source, followed by Verilog file. Now I am pasting the content that I have already written here. All okay. Let me save this. Save as generation of sine and cosine signals. CORDIC underscore DUT dot v. Save it. Even test bench, I need to save this, right? Save as. Altera within the programs. So .v, I have just saved the file now. Now let me compile it. Both file I am going to compile. Okay, compilation is done. See here, that model name I have given for test bench is test bench underscore CORDIC. Okay. Go to the simulation. Check for work directory. Within the work directory, see for the model name which is test bench underscore tb underscore CORDIC. Click on OK. Okay. Now these are the factors that I have assigned for the program, right? I need to add these all signals. Give a right click, go to the wave, add signals. So signals are getting added here. Let me enlarge it. Okay, now click on run. See here, this is the width. Okay, these are the inputs and this is the output, right? Cos underscore and sine underscore out are the outputs by, and these are the inputs. Click on run. So you can observe here the sine signal and cos signal are being generated in terms of binary. That is important. For the fixed angle of rotation and for the inputs given, you can observe the sine and cosine values in terms of binary. You can see here I have removed the test bench file within the Xilinx. Now let me go for the synthesis with respect to DUT. We are done with it. Generate post, place and route static timing completed successfully. Click on the main file. Now click on the synthesis part. View the RTL schematic. Click on OK. Create a schematic value. Okay, this is my actual DUT file where I have given the two inputs and a fixed angle, followed by the two output that will be generating is a cos and signal. Let me see the internal view of this RTL schematic. Let me zoom out. Here is the internal structure view of your CORDIC algorithm.